Good evening, everyone. Sorry, the green screen problem is still there. Well, I could probably, I don't know, it's got wrinkles. Maybe if I hung it from the ceiling, I don't know, it hates me. But anyways, there was a comment on YouTube about taking calculator and getting its output. So here's the calculator. Blah, 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 plus blah, 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 equals 105 apparently. Must have put in 53 and 52. Anyways, so getting its value, outputting it to a console, and then sending it back something random. Well, I did a little research. I read into this. Well, I didn't read into the topic. I read into the executable in Ollie. If you want to see that video, it's basically a stretched out, elongated, like searching for and ifs and blah blah blah, and well maybe if we did blah blah blahs. It was like 6 hours worth of video, but about 3 of those hours I was either AFK, on the phone, talking to somebody in here, stuff like that. I get interrupted quite often. Yeah, it's okay. But we are going to go over it right now. But when you look at this, you see a dialog box. This is what this is, right? It's a dialog box. And then it has buttons, control buttons. And then it has a menu bar with menus in it. It doesn't have a right click. Oh, it does have a right click menu, kind of. What is this? What is it? What is this? It brings up help. What is this? That's the equal button. So if we close that sucker out and open her up in Ollie, and let's remove any breakpoints we have. Nope, we don't have any. Okay, cool. And run. We have our calculator. So obviously when you put in 3 plus 3 equals, you see it returns 6 dot. We assume 6.0. It just likes to represent the decimal. I don't think the new version of the calculator actually does this. Let's find out. 3 plus 3 equals. It doesn't. Unless it needs to. So let's do standard. Standard old calculator. Yeah, it doesn't do it. And it gives you this like little string up here of what you're doing and all that crap. But we got this because it's 32-bit. And we got it from, come on, I minimized my windows. Bring them back. Okay, fine. Anyways, I got it from Windows XP 32-bit. And that's currently running in Ollie. So how do you update a text box? Well, a lot of you Visual Basic programmers or .NET programmers are saying, well, you just do control.text area dot text equals, and you set it. That's all there is to it. You just set it. Well, that's true in those languages, but this is written in good old-fashioned C. And they like to convolute things to where you have to call a function that doesn't. You can't just set it. What are you talking about, set it? You got to call a function to set it. Now, we know of a few functions, like if we search for intermodular calls, because let's get real. Names shows you everything that could ever be in the library. It doesn't necessarily ever have to be referenced anywhere. Now, all intermodular calls is any names that are referenced, are called, and how many. So if there's like, if it calls create dialog EX or whatever it is, I forget, 3 times, there'll be 3 in there. In names, there'll just be 1 of each, possible call. So let's click that sucker and sort by name. Now you get some of these that are unnamed. They're, in-program functions. And we see some stuff like this, but we're interested in things that set text boxes. Well, let's scroll on down. Draw text? Maybe. Doubt it. let's see here. Get items would be getting it. Get control item. Get control ID would return the ID of it after you got it. Let's see. So basically, in the other video, I'm looking through this and going, okay, how do you edit a control box? Well, set something, probably set. So first thing I did was scroll down to the S's. It went set DLG item int. Well, no, because we're dealing with a string. Because you have to remember that when we press 3 here, we see a 3 here, which is an ASCII character representation of 3, which is actually hex 33. And if you want to get technical, if you try to do mathematic stuff on the ASCII of 3, you would come back with, well, you go 3 in decimals. Hex is 3. But if you do 33, the string representation of it, which is in hex, decimal is 51. So all of a sudden 33 plus 33, or 3 plus 3, on the ASCII end of the world would end up giving you 102. So if someone asks you, what's 3 plus 3? And you say 6, and they go, no, it's 102. It's because they're adding the string character 3 to itself. Kind of like, there are 10 types of people in this world. Ones that can read binary and ones who can't. People go, but that's only 2 kinds. It's because 1, 0 in binary is 2. Anyways, so we know it's not an int thing. Text wide, maybe. Could be that. And if we break out Google over here, you know, our best friend Google, and we type in set DLG item text W, which you can see I've already looked into this. Let's make this a little smaller so you can actually see what we're doing here. Now, you can see it sets the title or text of a control in a dialog box. Great. Great. But that requires the ID, the numeric ID of the dialog item, and a handle to it, and then a string. Is there another way you can do it? Well, let's we could use the message set text, but even more simple, and I don't know why they do it like this. So after I looked into that and realized it wasn't the right thing, I was like, okay, well, we have set window text. We have that twice. Usually that's just to change the title, like on the calculator right here, this little title would be set window text, give it this hwin, you set that to whatever you want. It is getting hot. Alright, so, but upon further investigation, set window text, you see that it changes the text of a specified window's title bar if it has one. If the specified window is a control, the text of the control is changed. However, set window text cannot change the text of a control in another application, which kind of makes sense why they used it. Maybe they just felt like using it. Maybe the library that they used it in used to make it, when you typed, you know, control answer dot text equals, it just called that, because you can librarize things to work more like modern high level languages. So I put a breakpoint there. I just hit F2 and I was like, okay, let's 3 plus 3 equals, and it broke. And I was like, well, that was easy. And there we go. And you see that when we break here, we have text 3. Okay, well, that's not 3 plus 3. It's 6. And the registers don't look too interesting. We hit run, and we get a little error that says, that took a long time. Do you want to continue? Yeah, I want to continue. So let's do plus 3. Well, it broke. So we know that it's using it to write it no matter what, whether it's answer, whether anytime it's writing. And we see again that we have 3 here, and if we, you know, the set window text, the text is going to be 3. And there's nothing too interesting in the registers. This does actually point to right there. Yeah, continue, I don't care. And then when we hit equal, you see again it says 3. What the hell? You hit run, and it pauses again. Because now it's going to actually write the 6. And so at this position here, we know that the answer that we want is at, ESP plus 4. So the top of the stack pointer is the ESP, double click, and it shows plus 4. Well, right there. And that is a stack address. And you're like, oh, well, that's pointing where? Right here. So it's at ESP plus 20 is the actual bytes that have been written, the buffer that it's pointing at. You're like, okay. So we could put our thing there, could jump out, but do we have anything to differentiate as to, my glasses are really screwing up the focus, to differentiate between whether we're pressing 3 or equal, or if it's a second round of equal? Well, let's hit run. Yes, I don't care. Well, if we hit 6, we look at the registers, there's nothing different, nothing changed. Something down here changed, but we don't really want to watch the ST register. We really don't want to. That's a whole other set of commands that we've never really talked about on this, which we will. I think we're going to mess around with the XM extended instructions soon, because they're a lot of fun. And sometimes they are used more so than other things. So you hit run, and we're going to actually pause, do Alt F9, then we're going to click continue, and then we're going to find references to selected command and nope the shit out of that so it stops bothering us. Okay, so now when we hit equal, things changed, but it was just because I modified that. So we're going to hit equal again, but now we know the equal usually hits twice, so we hit run, and it hits again, and we got a little message, but it didn't pop up, it didn't bug us. And you notice the registers are all the same. It's, how are we going to differentiate between the button presses? Well, let's hit equal just by itself now, which would just add 3 to 9. And we see the EAX is now 4, and EDI is 4. Like, okay, cool. So that changes. We could compare EAX with 4, and if it is, and that's what we're looking for, right? Because it has our answer right there, and we hit run. It didn't hit twice that time because it didn't have to reference anything else. But if we hit +6, you see that it's a 3, and you're like, okay, cool, yeah, it's not 4. Great, that's different. Then you hit run. Okay, cool. And then you hit equal. Wait a minute, it's 3, but we don't have our answer yet. Excuse me. So we hit run and we let it pause again, and we see it is 4. But is this always true? If we started here, we wrote it, and we just checked for 4, it would work 80% of the time, but sometimes, for some reason, I didn't look into it because I don't care. It doesn't always set that to 4 and this to 4. So you look at that and you're like, okay, so let's just spam equal. Oh, it's 4, okay. Equal, it's 4, okay. Equal, it's 4. But trust me, sometimes it's not. And oops, I closed it. We'll run that. There we go. We're going to break there. 3, it's a 3, run, plus, run, 3, run, equals 3. There. So that time, let's hit equal. Plus 3, run, equals 3, 3. So that time it didn't change. And it's spitting out our answer right now. So sometimes it doesn't. It has something to do with how it determines when and how to do math or something like that. But I don't care. And I know what you're thinking. You're thinking, well, why don't you just start at the top of the function here? Because we checked that, it's, equals. Right there in EAX is our answer. Sweet. And you see that in ESI you got this weird ass number. Okay. Well, what happens if we hit 3? Or plus 3. You're like, okay, so ESI is 7F, is putting 3 in there. Okay, we run. You hit equal, and you see, okay, there's 70. It's not our answer yet, so that's the first run. And then you run, and it's this weird number in our answer. That'd be easy. You check ESI if it's greater than, 1,000 or so, because they're not using that many identifiers. Then your answer's in EAX. Just pop it out, write it, do whatever you want. Well, that's too easy. Sometimes you don't have an easy, you know what? You gonna stay focused now? Huh? Okay. Sometimes you don't have an easy option. Sometimes that doesn't present itself. Sometimes you're down here in the middle and you're like, okay, on this one line, I have what I'm looking for, easily referenceable. I can take it out. We're okay. But that one line may be, not so, like, it's the easiest, but it's not easy. You're like, okay, so we F8 through, and we're not going to go there. And the DLG item, this all changes. You're like, okay, string length. Okay, so our answer, when we're here, is being referenced at ESP plus 10. Like, okay, cool, it's right there, and that's referencing right here. And okay, and ESI is still that big number. Okay, cool, so that would work. But as soon as we get to here, ESI is different, and if we break right there on all of them, yeah, I know that since I had to restart it, the patch is gone. Continue. If we hit, plus 5, well, ESI is exactly the same as our equal was. There's no factor. And you look, okay, there's EDI is weird. Let's watch that. Equals, and EDI is exactly the same. You run it, it hits the second time. EDI is a little different, but that's very specific, and you can't count on it always being the same or within some sort of error region. So right here, we can count on ESI being set to way over 1,000 and the rest of them being way under 1,000. Gives us a big margin of error if that's all we had to go off of, and that's where we're actually going to do our patch. If you were presented with something easy, you'd take it, but for this tutorial we're not going to. You come down and you hit here and you go, okay, so it's all referenced here too, and you can do it here, but again, this is where we'd be going off of that 4 that's sometimes a 4. And so what we want to do is, again, pause, Alt F9, I'll continue, and then we're just going to search for all references. Oh, find references to, selected command, double click, and we're gonna want to just not let that, we don't want the message beep, we want to go over it. So we don't want to land here, which is from here. So we want to land here, or here, or here. There we go. So we're gonna jump. Actually, we could just nope that, but we're just gonna jump here every time. There. That should get rid of the beep and all that stupid jazz. Equals. Wait. Right here, you see, if we pause right there on string length, that it's at the top of the stack, our answer. And let's hit run now. Good, no beep, no message, we're good. Because that's going to get really annoying for the rest of the video. So right here, we're going to use this address, and we're going to jump out to some area. Let's find somewhere that has view executable modules. Let's look for calc. We were already in it, I know. I want view memory map is what we want. And let's look for the PE header of calc. And let's look for Scroll on down here. There we go. Areas that are read writable, which usually is, oh, right here, code, execute, read. Oh, we don't have write. We want write. We can just change that. I think is it 4 right here, does it? Data, execute, read. No, I think it might be C, actually. Nope. Is it 8? There's right. C. Uninitialized. Link remove. I don't know. Let's give up on that for a second. Analyze. But do we have any? So we have read write and initialize read write here. So C40 initialized data read write. Let's just characteristics. Header. PE header characteristics. Yeah. Come on. We just don't want it to yell at us when we're writing to an area that you're not supposed to be able to write to, so it's just going to change it to allow us to, and I can't remember what it is. You could probably set it to FFFFF and just see what it... Initialize data, read, write. Code, read, write. So C20. Code, read, write. No longer execute. What was this? 4? No, it was an 8. I think. No. 6? Well, what the fuck was it? There we go. 6. Code, execute, read. Right. F. That works. Code, shared, execute, read, write. And that is in the text region, which starts at... well, that's not very helpful. So it's virtual size, virtual addresses, 1000, and then it goes down. Size of raw data is huge. So we're just going to set them all to this right here. So that no matter where we put it, it doesn't matter. I could find somewhere and then just executable image. I think this one we actually need to change also. There you go. That's every characteristic known to man. Sounds good to me. I don't think that one matters at all. Edit, undo. Okay, so we'll see if that works or not. And so we're here. Now, first thing we need to know is we're going to use a call, not a jump, for one reason only. With a jump, so if you have a section of code that's, like, I don't know, 90 bytes long, and the very last line has to jump back to here, well, we are going to know this address here, and then we could calculate this address here to jump back. And then you have to retrofit it to the section of your code. You'll see when we get there in your program. But it's much easier to just write a call and then use return. And I know what you're thinking. If we overwrite these, we have to call them at the end of our code, right? Right. And if we try to use a return, but I see there's a push there, won't it try to return to that value? It would. So before we end, we'll actually pop off the return, do our pushes, push the return back on, clear the register that we used, and then return back. What's left on the stack will be our pushes. that we want to be there. So let's jump to it. Let's go ahead and scroll on down to the region unknown, and I hope that this is writable, but I doubt it's going to be, because half of this probably doesn't actually exist in it. It's just here, like virtual. So we want, I'm going to tell you ahead of time, we want 1 byte, because we're going to use kind of an old school byte set messaging system to where, like, once the calculator gets there, it'll change the byte, and then our program will be listening for that byte change, and then it will do its mods and change it back, and then the program will continue. Because we're not actually going to make a DLL. We're not going to hook the program. We're not going to inject a DLL because we're going old school. We're starting out. Basically, I wanted to do a Codecave tutorial, and so that's what we're doing. And I wanted to kind of stay away from like named pipes or like my other hooking system using messages to send data back and forth. Just doing, read and write memory, which is slow, I understand, but we are going to do that for now. So we're going to use 1 byte for our message byte, and then we're going to need enough space to store an address, so a D word. So, 4 bytes. Well, not a D word. Yeah, D word, 4 bytes, 8 bits. Yeah, derp. And then we want to jump to this address here. So edit, copy address, hit the minus, and we're going to say call, wait, before we do that, let's open up a notepad. Always have a notepad handy. This is the address we want to jump to. And when we're done, that's going to need to be executed. And we know that this is 4 bytes here. A call takes up 5. It's 1 byte to say it's a call, and then 4 to jump to the location of however far away you are. And then it's going to use up this 8B byte. So then we just have a random FO floating. So we are actually going to nope that. It's going to automatically do it for us. So we know that we're going to have to also put that at the end. So now let's go ahead and do that. Call blurb. And you see it updates it, nopes it, all good and dandy. And we're going to jump on over to it. So what's the first thing we need to do? Do we need to restore, save all the registers and all that? I mean, is it that important? What if we just don't? Well, could cause some issues, but let's hit equal. And we're going to land here, and we can't run from this point. But we see that EDX is 0 and EBX is 0. Knowing that, we can use them as long as we set them back to 0. But let's think about that for a second. If we do XOR EDX, EDX, well, that took 2 bytes. And then we're going to have to do another 2 bytes to XOR EBX. So that's 4 byte total. Whereas instead we could just do push AD 1 byte and pop AD 1 byte. Yeah, 2 bytes versus 8 bytes. 4 times less. So let's go ahead and undo that selection. Perfect. Control A to clean things up a little bit. And let's jump on back down here. So here's our section of stuff. And you notice it grouped it all now. Because it's like, oh, it's this is code, right? It's not just data, which that's a good sign. That means we might be able to write without it yelling at us. So the first thing that we want to do is push AD, right? No! Why waste bytes if you don't have to? Focus. Clearly it wasn't the glasses. I'm going to put them back on, otherwise I'm going to get a headache. So, apparently this video is a half an hour long already. That sucks. But, so we're going to get here, and we know that we want to check ESI to see if it is the correct equal, to see if we even want the output. So we're going to do compare ESI with, well, 1,000. Jump if not greater. Jump if less than or equal. Works just fine. We'll do that. And we're going to say jump on down to 10136DE. Probably not the right address, but hey, we might get lucky. Now, otherwise, come on down. Right? Come on down. So now, do we want to save our registers? Do we? Do we need to right now? Yeah, go ahead. It's fine. Push AD. So we know that we want to be able to reference this byte and these 4 bytes. Well, if we're dynamically allocating space, we're going to have a different address each time. How are we going to be able to do that? Man, that green screen is pissing me off. Select this color. That's better. Yeah, I'd rather me have a little trickle than the whole thing be fuzzy. Anyways, it could be a different address. So we're going to need to know where we're at. Now, there's a little trick. If you know how a call works, it's common knowledge. So a call, when you type, call some address, it doesn't say, it's not like saying go to address. It doesn't look for that address and go there. No, that would be dumb. Because it would have to, locate the address and move the... And you're like, well, couldn't it just change EIP to that? And it's like, kinda. But instead of doing that, the way a call works is it says go to this far up or down. So, for example, if I want to call an address above me, 10136AF, it's going to be negative. E8, E9, F, kind of negative, right? And that is saying, well, it's up there. It's up there. It's negative. If you want to go down, say 10136C8, oops, 36C8, it goes, okay, it's 2 down. It's 2 down, right? It's right down there. So what we want to do is actually call the very next line, which would be C6. And you'll notice that it's 0, E8, 0. And what happens when you do a call? What's it put on the stack? A return address to the next line. Well, we're calling the next line, so it doesn't matter that we're trying to return to it because we're already there. So what you do, you pop it to EAX. You know where you're at now. Because EAX is going to be equal to this address right here. And we need to know where this byte is. Well, it's minus 17. Cool. Now what? Well, we need to LEA, EAX, not EAX, EDX, and it'll be EAX minus 17. Cool. That's going to load in this byte right here. But what the hell do we want to put in it? Well, we don't really need to do that, do we? Because we can reference it, just like that. We don't need to load it into a register. So instead, what we want to do is come up here and hit F7, compare ESI. We see that it is greater, so it's not going to jump. Then it's going to do our push AD, loads all that junk on the on the stack, and we're here. Our old one was here. No, it's not. So yeah, it's right here. And then we're going to do a call, and then we're going to do a pop EAX. So when we get to this point, the address of our answer is now at ESP plus 34, not 10. So what we want to actually do is move into those bytes up there. So D word. Are we getting ahead of ourselves? I think we are. So first we want to do move EDX D word at ESP plus, what do we say, 34? Is that going to work? It does. So why can't we just put in right here D word EAX minus 17? Well, it's going to yell at you. You can't go from an address to an address. You have to go from an address to a register or a register to an address. So we're going to go ahead and put that into EDX. Great. Now we can go move dword at EAX plus, nope, minus 17 EDX. That's going to work just fine. Well, let's find out. We hit F8 and we see that this now contains the stack address. Well, we want what's at that address, right? Do we? No. Because we want to read that address later. If we put what's at that address, we're going to be putting in, 00370032, and when we try to reference that, it isn't going to work. So we want to, yeah, that's right. And now when we hit F8 again, we might get an error that says access violation, but we hope to see the address written right there. And we got an access violation. Oh well. And we also note that our stack's all screwed up now. So if you need to reference that from this point forward, you're screwed. You have to restart, which isn't too big of a deal. You just binary copy that and call it good. But for us, that's good enough. So now what do we want to do? Well, we want to set that byte to 1, our check byte, compare it to 0. If it's equal, jump out. Well, do we have to use compare? No. We can test. Does the test take up less space than compare? I believe so. Let's find out. So let's go move into EAX. Well, if this one was minus 17, then this one's got to be minus 18, right? 1. No? Ah, right. Move into byte. Got it. Now we want to compare. Well, we're going to try them both. Compare byte at EAX minus 18 with 0. Okay, that takes out 4 bytes. Test byte. Well, that doesn't work. You have to load it into a register to do that. Can we just do this? Nope. Well, okay, well I guess we're done with EDX, so let's LEA EDX. Bam, that'll work, right? And then we'll do test byte at EDX, right? No. Against what? 0? Hey, that works. Now, was I just typing wrong? Let's try that again. Test byte at EAX minus 17 with 0. What do you know? It works just fine. And it takes up literally the same amount of space, 4 bytes. So it really doesn't matter. You can compare, you can test, doesn't matter, whatever is easier for you. So we're going to compare it with 0, and we're going to jump if equal out of our loop, which we're going to say is going to be at 10136E8. We're not sure. We can change it in a minute. But if we're in the loop, we want to sleep. Is there a reference to sleep? Man, I hope so. Search for names. Sure, since you can see that. You couldn't see intermodular calls. Sleep. What do you know? There's a sleep. Now, is it used? Find references. By golly, we got one. So we literally copy, come back, paste, right? Right? Well, that doesn't work. You got to get rid of this little and symbol. Then it works fine. Well, we're missing something, aren't we? You got to push, how long you want to sleep for. Well, the problem with that is sleep, after it runs, is going to overwrite EAX for sure, along possibly other things. So, first thing we want to do is push AD, because we don't want to have to go through getting our EAX again. And then we're going to push, 60, and then call our sleep. And obviously, this address is going to be different. So we're actually just going to say call dword at EF yeah, EF, BE, AD, DE. Is that right? We'll find out in a second. Yeah, that's right. So you see here in our actual code, it says dead beef. Perfect. And then we're going to go ahead and do a pop AD. And then we're going to jump to our compare. 101, 36, D2. Well, you say, our loop never changes it. Our other program will change it. Our program will change it when we are done doing what we're doing with calculator, which is faster than you think it would be. And so let's check our jump out. Well, we overshot a little bit. We can go E4. E4. Perfect. So when we're done with that, now what? Well, now we need to clean up, run our stuff, and get the hell out of Dodge. So first thing we want to do is pop AD. And then we want to pop EDX, because we know it was 0. And then we want to run our push D-word as a pointer SS blah 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 paste. And then we want to move, come on, let me type, move ESI EAX. And then we want to just return. Great. Wait, that doesn't work. First we have to push EDX and then go XOR EDX EDX and then return. So what that is actually doing is restoring the registers to where they were when we first came in. And then it's going to pop our return value to EDX, do our push and our move, which the move didn't have to be there, but the push did, and then push the return, zero out EDX back to where it was, and then return. And so our jump up here needs to actually go to E5, not E4, because this is before the push AD, so E5. And there you have it. So we're going to compare. If it's less than, then we're just going to jump. Well, apparently I bodged that. Right here. 10. Oh, one, wow. Yeah, we really bodged that. 101, 36, E5. Yes. So you see that takes up a whole lot less space when it's not a far jump. It's a short jump. And we're going to go ahead and move all of this up, and it's actually going to change. Edit, binary copy, edit, fill with nopes, drag from there, edit, binary paste, scroll on up there, and we have our call to right there. That works. We have our jump that jumps out to the right place, but now this needs to go to E1. There we go. So that jumps out to our pop and returns. So let's do an analyze and see what it does. Well, that cleaned up quite nice. You see that we have a call to here that's referenced right there. We have a call here that's from up there. And this would actually run now. So let's edit, highlight all that, edit, binary copy, and go ahead and paste that in right there, because that's our code. That's it. Because what we're going to do is, in our program, is we're going to wait until this is changed to a 1. When that's changed to a 1, we know that this now holds the address of the buffer. We're going to write our own string in. Then we're going to set that to 0, resuming this thing's function. Sweet. So let's hit run and see if it dies. Nope, didn't die. An unknown error has occurred. All right, I'm cool with that. I don't care. Equal. Okay, F8, and it's gonna try to step over, and it's not gonna work because it's hitting that access violation every time. So we're gonna actually use a spot on the stack here. We'll use like well, let's come down to it when we actually do it here, is do right here equal F7, come on down. Okay, so instead of going to EAX minus 17, we're going to go to ESP minus C. And that uses up even more space, it looks like, because our move to 0 is to here is not fitting now, which is okay because we'll just move this down. This is just for the sake of demonstration. Edit, binary copy, edit, fill with nopes. We want to go move, which this actually won't work either. So we use ESP minus 14 for that one. Move byte ESP minus 14 1. Now we'll go edit, binary paste, compare byte at ESP, and this might take up more space. It does. And then we'll go edit, binary paste, and we'll grab this and go edit, binary copy, edit, binary fill with nopes, edit, binary paste. So we're all back up to snuff there, but this is screwed up. We need to go to E6 now. Everything else should be fine. As a rule, you can always write to the stack, but if you write to the stack in the wrong spot, you could cause, frame errors, stack errors, overflows, stuff like that, but we're not too worried about it, as you could tell. So that's going to do that, then it's going to change that, and so let's see if this works. So bang, it did write it right there, you can see, and then we see the 1 show up right there, and we're going to compare it, and it's not taken. So we're going to go into this loop forever until our program changes it. So we're going to go ahead and come over here, new origin here. When we finally come out of it, it's going to go pop AD, pop EDX, push, move, push, clear, return. And we're right back. Sweet deal. So in our code here, we need to make this, fit in things that, like it. Some string format. So we're going to go edit, replace, space with -x, replace all. We're fine with all that. Control C. Well, you know what? Yeah, that's fine. I don't care. There's our dead beef, which we're going to need to remember. So let's go ahead. And I want to actually compare this with the code that I had written before, because it was actually a lot different. So that we can't forget the bytes at the beginning. So you see that this has 8-1, but you have to remember we have 5 nopes at the front. You gotta put those in. Just like that. So it looks like our code might be identical until we get down here, and my original code was 2 bytes longer. Why? Come on. Because I used 1 register. I used EDX. I didn't do push AD and pop AD. I used 1 register and then I just set it back. But we'll use the updated code, which is good because we're going to have to modify our stuff in here just a little bit. So we know it's 2 bytes off, but is it 2 bytes just overall? Dead beef doesn't line up anymore, does it? It does not. Dead beef is 2 bytes shallower. That's good to know because we're going to need to know where to write that when we get there. So this you've seen check hotkey, you've seen the get address. We did add something to the get address, and this is if it finds a pattern, you have given a mask and the handle, That's all the same. But then we have write bytes equals 0. Well, if we set write bytes, come on down here, if write bytes is not equal 0, mem copy write bytes mem section a plus I minus 3. So what that does is, if we want to return the last 4 characters, say an address to a call, then we just say write bytes 1, and well, write bytes is actually a pointer to a D word. So you give it the address to your D word, and then it writes in the address. Easy peasy, no problem. And by what it does is it finds it, goes back 3, copies 4 bytes into your D word that you provided so nicely right here. Well, character pointer, D word. And yeah. So then hex to ASCII you haven't seen yet, but what that does is, so like I said before, you have 33 represents 3 in ASCII. So to get there, say you have an address as a string, you have, E5 and, well, we'll take dead beef. So you have DE. Well, DE to us means a byte, but in a string, it's a D and an E. So what you're actually doing here is you're taking the first byte and the second byte and casting it in as 2 characters into a character array, and then you're calling string too long, I believe that's what it stands for, on it, and you're going to store it in what looks like stop, I don't know, and it's in base 16, and then it's going to return the output of that guy. Easy. So you'll see where we need to use that. We have our code, and then we have something called our call. Well, you should be able to tell by looking at it that that is where we're going to patch in here, right here. That's our call. See, we got the E8, the address, and the 90. Well, we have to retrofit the address because it could be different every time. We got to find it. Then we have some random words. With this, 2 plus 2 could equal chair. We have our running Boolean again. Then we are finding the window, getting the handle. This is all from the last video in the TeamViewer flip you saw. Excuse me. And then you see that we open the process. That's all the same. Then we define sleep address as a character pointer. And then we call get address with a lot of junk. And you notice that the mask, the last 4 are question marks because that's our address, and it doesn't always have to be the same. In fact, it could always be different. But we want those bytes. So we give it the character pointer of the address of our sleep address, which that could have been avoided by defining that as car and then just giving the address. But I didn't do that. Didn't want to. I guess it doesn't matter. And so when that executes, we don't even want the return. It doesn't matter what the return is. We don't want that address. We want what's at. We want the 4 bytes next after you found that. And so that's going to put it in sleep ADDR. And it's going to output it, and then it's going to go mem copy our code plus 44, what's in sleep address, for 4 bytes. So what that's doing is, remember dead beef? Well, dead beef represents the holder for our call to sleep. And we know that it's actually 2 bytes shallower now, so we can change this to 42. And then we have our code, it's going to print it out. And then we have D word base of our code. Okay, that kind of a little confusing. But what we're doing here is we're going to open up that executable, allocate 100 bytes of space. We don't even need that much. We need literally like 60 or something. Not even. And we want it to be committed memory, and we want to execute read write. And then it's going to output allocated memory at the address, which this returns the first address of the allocated memory, which does not actually allocate the space until you reference it or start to use it. So if you allocate a bunch of space but never use it, it won't actually do it, which is actually cool. I don't think it always did that. So then we have patch call at. That's where we want to put our call in, right here. So we grabbed this, much like in TeamViewer Flip, and we made, in here, we have the bytes that we're looking for, and then we have a mask. And then in this, we just have the process, and we don't want it to give us the next 4 bytes or anything, so we don't define that. Since it is defaultly defined as 0, it means it's optional. You don't have to give it. If you don't give it, it's going to be 0, and down here we check to see if it's not 0. If it's not 0, then do other stuff. If it is, don't worry about it. And so that's going to find the address that is right here and give it to us. All right, so now we have an address. But here's where hex to ASCII comes in, because these are ASCII characters. This is XEB. We're saying we want the hex value of EB. We don't want you to print an EB. We want the hex value of EB. But I can't just plug in. So when this executes, we get call bytes, right? And then we need to actually get that into where we can patch it into our little dude here. Because since these things could change, we can't do like we did in TeamViewer Flip. Well, we could kind of do it like that, but that was more like find this, make that a pointer, and patch it right there. But we need to actually do this patch a little bit differently. So, or I just wanted to show you this. So when you grab that address, you got it, great. Well, it's in a D word. We need to be able to put it into a string. And so we're storing it in a character. And we're gonna do sprintf %08x, which is going to print it in there as ASCII characters. I know a lot of you are saying this is an extra step, we didn't need to do this. That's correct. I just wanted to demonstrate it because there are times when you need to do this. Like with, well, yeah, we could have just done memcopy, but anyways. So we are putting it in call bytes as a string, but now we need to get the actual hex representation. You go, well, you already had that. Yeah, I know. It's fine. Now, when we do this, it's going to go through it backwards, 8 minus I plus 1 times 2, and then it's going to go 8 minus I times 2 plus 1. So it's going to go doo, 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 doo. First, second, first, second, first, second. And we're going to loop through it 4 times because we want 4 bytes out of our 8 characters, which I know we already had up here when this returned. That's fine. So then we're going to have our call code. Well, that's why we had to do it. Because the code that we're writing is in a string. And we can't put these in because we have 4 characters, or we have 4 bytes. That would only be 2 characters. It wouldn't work. We need the ASCII representation so we can put it in our string. And so our call code is going to print out here. And you notice that here we go our call 1 plus I, because the 1 is the E9. And we didn't want to overwrite that, obviously, but we needed to, let me move that camera down. Well, I guess can't move down any further than that. I'll set up a little. But we needed to be able to put that in there as part of the string. So that's what it's going to do here, is it's going to grab each one, modify the string. Now, could we have just said, we could have done byte by byte, it's fine. We could backwards. We could have taken patch call at and then done, 4 and put it at 1, and then done 3 and put it at 2, and put 2 at 3 and 1. Well, 3, not 4. And then 0 at 3 or 4. That would have worked fine because we're referencing the actual bytes. I think it would have worked fine. I'd have to try it. But that takes up, more space. Some could argue. Maybe not. This is kind of almost a video on itself, which we might do because I could try to explain it a little better right now, but it would take up too much of this video, and this video is already an hour long. So we're going to move on. What that does is it grabs our address, converts it to a string so that we can add it to a character array. Make sense? Because if you did it the other way, you would get individual characters that were different. So then what we're going to go ahead and do is open our process. We're going to write our code first because we want our code in place just in case this call gets called, at some point. We want our code to be ready. So we write our code and then we write our call. And then we have a read address dword, a test byte, a value as a character, a new value as a wide character. Because if you remember here, this is in Unicode. If you look at this in the dump, it's 30370.0 space 00. A Unicode string doesn't end until it hits 00. And so we want to make sure we're writing back a Unicode string. I think if I zoom in, I can move down more. Okay, can we? Zoom in, down. Other way. Yeah, that's good enough. Anyways, so we want to, the new value needs to be in Unicode, which if you look up here, these guys aren't even stored to Unicode. Whatever, it's fine. So we, while running, read the process memory at our test byte, one byte. If test byte equals 1, which means we've hit the loop, we've set it to 1, then set test byte 0 equal to 0. And then we're going to read process memory from the base of our code plus 1, because we remember that the base of our code is our test byte, which we see here, base of our code, test byte. Plus 1 for 4 bytes is the address of where that return value is stored now. So then we're going to read that memory for 4 bytes. And then we're going to go ahead and print out that address. And then we want to read the memory at that address into new val, which that's actually incorrect. So that's all flipped cattywampus. But we want to read it into new val because we know it's Unicode. It's bad naming for the size of new val. We don't want to overload our buffer, but whatever. And then we call WCS to MBS. So wide character string to multi-byte string. So value, so the multi-byte string first is our destination. Our source is the wide string for the size of value. Why not? And what that's going to do is take that, what we just read, and put it in value as a regular old character string. And then we printf got blah value, string copy value, random words rand mod 10. So it's going to pick a random word out of this array. There's 10 of them, which rand mod 10 is going to give you a value between 0 and 10. And it's going to say writing value. Then we call this again, well, now we call it the other way, multi-byte string to wide character string. And we do the destination new val, see now it works, source value for the size of new val. And then we're going to write the process's memory at the address that the buffer is going to spit out the new value for the size of new value minus 1. That one little extra byte at the end. And then we're going to write the memory at the test byte, which is the base of our code, we remember, 1. If test byte equals 1, set it to 0. So in our code, we're checking it for 0, and I think in the old code, I initialize it. No, I don't. I don't initialize. Oh, yeah, we check for 0, and then I don't actually ever set it. But we want to set it back to 0, and this works with if it's 1. That's fine. That all works. So let's go ahead and then it's going to check for the hotkey plus X and see what happens. Then at the end, when you kill it, it frees that virtual memory, but we don't ever get that far. So that compiled. We didn't get any errors. Got some warnings about our character strings and all that shit because nobody uses character arrays as strings anymore. And if we rerun calc here, okay, whatever. View int3 breakpoints. I'll go to not that one, but over here. It's disabled, and that's fine. We don't want it to be enabled because our program won't actually find that address if you have a breakpoint, because it actually inserts a int3, hence it being called an int3 breakpoint. And if we go ahead and run this, we see allocated memory at blah, sleep address is here, our code is now this, and we check for dead beef, we don't see it. We should see, yeah, FF1540100001. And so this should actually work. So let's see what happens if we do 3. Okay, so our call is here now, you see. And obviously, we hit 3, it didn't crash. Okay, so plus 3. And now we want to actually put a breakpoint here and do equal. Now, it's not the first one. You see ESI is 70. We'll hit F9. Now, this one should match. So we'll hit F7, and we're going to compare it. It's not going to jump. We're going to push everything to the stack. We're going to call the next address. We're going to pop that. We're going to move EDX, the pointer to our answer. And then we're going to move that to our address that's right here, hopefully. And it gives an access violation. I don't know exactly why. Oh, right. EAX minus 17. EAX is, okay, so since all that got changed, this here, EAX is going to be at this address, and minus 17 is way too high. So it's actually minus 13 now. Minus 13. And you see that that changed from E9 to ED. So we're going to come into our code up here and find, what is it? It's 8950E9. So we're looking for 8950E9, and that's going to be ED. And then we know that there's another one just down below, it should be right there, and it is 78E900. We see 78E9, and that should also be ED. And we know that this minus 18 is obviously going to be wrong. And we now know that we aren't referencing the top byte, but the one below it. So the top byte is minus 13. We actually want minus 12. So that would actually be not ED, but EC. Or EE. No, I did 18. No, I didn't. I did 12. EE. Yeah, correct. So this here, our code, ED, would actually be EE. ED would be EE. And then the following E9 wait, that's not right. So we're going to change that back here. So that one's EE. Then these two reference the same one, which is minus 13. Which is going to be our EDs. And they're going to be E9s. Oh, they should be. Okay. So this one here would be an ED, like I just had it. And then we are going to look for an 87.8. Another one should be directly below it. Oh, right above it. So 8050 C6, that one is EE. And then we have an E8 here that should be an ED. So yeah, is that right? Yes, C640ED. ED. Okay. So now when we come back in here, after we get this error that we don't care about, whatever, continue, unknown error, I don't care. So equals, we're going to hit F7, and we are in the right one. So it's not going to jump. It's going to push all that up there, call there, move there, do that. Now you see it wrote. Perfect. Our address is there. It's going to change that to a 1 up there. Sweet. And right now it has the address. Our program can do whatever the heck it wants. And you see that it is. And it's getting, you know, what we're writing to it. And it's going to loop because, well, we're not letting it change that byte, even though it probably is in the background. So that's working. And then it's going to loop forever. So we're going to hit run and hit continue. Because if we just let it run outside of the debugger, we know it's working. That it should set that, but it's actually not. So we are comparing it against 0, and we're setting it to 1. So we actually want to set it to 0 in our program, which we should be doing. So let's check our little thingy here. If test by is 1, go ahead and do all this stuff. That's fine. And at the end, change test by to 0. So let's see if it was just because we had a bunch of breakpoints and such in there that it didn't want to work. We're going to go ahead and close this guy out, run it up again, and we're going to do 3 plus 3 equals, an unknown error has occurred. We forgot to recompile. X Go back, run. Got that there. Let's go execute, compile. There we go. So now if we run, those should be fixed, and we should be able to go 3 plus 3 equals, and you see that it's in this never-ending loop where we got 6, our answer, we wrote dog, but we're never telling the program to come out of that sleep. Well, let's figure out why. Search for name. Actually, we can just hit pause. It should stop us right in the middle of sleep, but it doesn't. Run. Search for names. Set. You know, we could probably hit stop on that. And it would probably just, well, I don't want to screw that up too much there. That should work. Set window text. So we know that we're in this right here. We could pause, and for some reason we're not writing to that byte. Or we are. See, you see that it's an 01, and we're trying to set it. Oh, I set that to 0. Now we want to write test byte to it, which is 0. My bad. For 1 byte. That makes a lot more sense now. Exit. Execute compile. And I'm so confident that this is going to work now that I will just minimize, close. We gotta recompile because we got permission denied. There we go. Minimize. Run calc. Run blank. No debugger needed. 3 plus 3 equals. Got 6, wrote dog. There you have it. So, in the end, and if you hit equal, we'll get 9, they'll get babies. We'll get 12, they'll get chair. And we can just keep doing this over and over and over. So in the end, we got there. I had one little hang up because I actually ended up changing the code on video here, just by 2 bytes or so, but then I had to think back of what exactly we were doing. So you go 2 plus 2 equals dog. Dang. Clear. Chair! Look at that, we got chair. Look, clear sets it off. Clear and CE, so we could do a little bit more stuff to, you know, make sure that it is equal. We could actually look for that specific value, but I didn't really feel like doing that. So I hope you learned a little something here. And not that I forget things, because everybody does that. Especially when you prepare something and then you want to code through it while showing people at the same time. There's a million different ways you can do something, and you're bound to change something along the way. But the base part of it works. 3 plus 3 equals run. Thanks for watching. Rate, comment, subscribe. If you have any questions about this, I know that we did move kind of quick, and that there were some fuzzy areas, especially where things differed a little bit from when I prepared them. And I was like, oh, duh. And then I was like, that whole 1 byte thing. Sorry about that. You guys are screaming at the screen going, you're an idiot. Which I do to people all the time. I'll watch a video and be like, oh my God, do you know what you just did? And now you're trying to figure out why it's not working and you're not figuring. Yeah, I know. Could have saved 10 minutes, but yeah, this doesn't set the value. No, this does, and it's 1 byte. So, again, thanks for watching. Rate, comment, subscribe, pass it on, do that stuff. Play around with it. If you want me to throw this in Dropbox, I totally can. Actually, I will. I'll zip this, the code, the whole project folder, and the calculator executable also. I'll zip that up and I'll throw it on Dropbox, and there'll be a link down below. Thanks for watching.